We're going to continue working with this problem. This graph gives velocity. There are a set of problems that are not that computationally difficult, but where it can be difficult to pick up on the keywords that tell you what the problem is asking for. Remember from previous lessons that there are formulas for what we call net distance traveled, total distance traveled, average velocity. And then a long time ago we did greatest distance from the origin. And these formulas look very similar and people get them very much confused. You have to make sure to pay attention to the keywords. So net right here, net distance traveled is just our plain old integral. This means that positive area is going to be positive, negative area is going to be negative. Total distance traveled means we take all of the different areas that we're working with, we make them all positive, and then add them up to get that integral. Average value is just the plain old integral, no absolute values. We've got the 1 over b minus a. And then greatest distance from the origin is really similar to total distance, and people like to get them confused, except for greatest distance we take the integral and then we take the absolute value. So what this would do is it would add this up, so we'd first add this area, then subtract this area. And then whatever number we got there, we would make that be positive, even if it was negative. Whereas in this one, we're going to take this positive area, we're going to make this positive, and then we're going to add them up. So these two, this is going to be a much larger positive than this one, because here we subtracted and then made it positive, and here we made it positive and then added them. So the keyword for this one is total distance traveled, and the keyword here is greatest distance traveled. Average right here tells you you're going to be using this formula. So let's start off what is the net distance traveled from t equals 4 to t equals 7. Okay, so we're going to look for our net distance formula. That's just the plain old integral. 4 to 7 v of t dt. We're remembering that this integral means area under the curve. I should make that signed, area under the curve. So coming back up here, let's see, 4, we've got 1.5, got negative 1.5, and negative 3. So v subtract b 0, negative 3, and we are measuring in meters for distance. So that just means that at the end of the day we end up 3 meters to the left, or actually at the end of 7 seconds, we end up 3 meters to the left of where we were at time t equals 4. So this is in contrast with what is the total distance traveled from t equals 4 to t equals 7. And we always start off with our formula, so let's actually label this net distance we're going to take the absolute value of the velocity and then add them up. So here we're taking the absolute value of each area that we work with. So here absolute value of 1.5 is positive 1.5, but here this is going to be absolute value of negative 1.5. So positive 1.5, positive 3. So here we've got 1.5 plus 1.5 plus 3, 6 meters. So what this is saying is it's saying that first, when we at time equals 4, we were somewhere, and then we went 1.5 meters to the right, and then we went 1.5 meters back, and then 3 meters back further to the left. But both of those 1.5s count. We went 1.5 plus 1.5 plus 3 to find total distance, whereas net distance is just saying where were we in relationship to that point. So we went 1.5, but then we undid that, so we're just counting the negative 3 that we went to the left. This absolute value is in contrast to another absolute value that we work with. So that is this one. What is the particle's greatest distance from the origin on the interval 4 to 7 if position at time t equals 4 is 1. Okay, so we're looking for greatest distance from the origin, so we're talking about compare absolute value of any maxima to absolute value of any minima. So first we have to figure out where those are. So we'll do our sign charts, maxima and minima. That's the increasing, decreasing line. That means velocity. We need the plus minus line. So looking over here, we're starting at 4. 4 is positive until 5, and then negative up through 7. So increasing, decreasing. It's going to the right and then back to the left, which makes sense. Okay, so we need to check here, here, and here. So here we're checking what the position is. We just don't care whether it's to the left of the origin or to the right. So we know that the position at time t equals 4 we're told that is 1 meter from the origin. The position at time t equals 5 is going to be that same position at time t equals 4, plus however far it moved from 4 to 5. So from 4 to 5, added 1.5. And we know what p of 4 is. We're told that p of 4 is 1. Okay, and now we want p of 7. So that's again going to be p of 4, which we know, plus the integral from 4 to 7 of v of t dt. This is just the normal integral. We haven't done anything with the absolute value yet. So p of 4 is 1, and then integral from 4 to 7. This is just normal, so we do 1.5 minus 1.5 minus 3. So 1 minus 3 is negative 2. So now we're going to compare the absolute values. We just want to know, we don't care if it's to the left, negative, or to the right, positive. We just want to know the greatest distance overall. So This is already positive, so absolute value of P of 4 is 1. Absolute value of P of 5, let's see, there's the absolute value symbol, is 2.5. Absolute value of P of 7 is absolute value of negative 2 equals 2. So this is our answer because 2.5 is the largest of these numbers. Right there. Now, all of these are in contrast to average value. Again, always make sure to set up our equation. 7 minus 4, integral from 4 to 7, v of t dt. Notice there are no absolute values running around here whatsoever. We simply have to do 1/3, and then, let's see, integral from 4 to 7, 1.5 minus 1.5 minus 3. So negative 3 divided by 3 is negative 1. We're working in average velocity, so the units are still meters per second. This same sort of thing can be done with an equation. So let's take a look at that. So let's say v of t is t squared minus 4. And let's do our usual meters per second. So first, let's find the net distance traveled from t equals 0 to t equals 5. So always set up your equation first. Net distance is just where did it end up. And that's just the normal integral from 0 to 5, t squared minus 4 dt. In this particular one, we're allowed to use our calculator, so I'm just telling you that right now. There's nothing in the problem about it, but we are. So we'll just do our normal math 9. Let's see, variable squared minus 4, comma, variable, comma, 0, comma, 5. Pop that in like normal, 21.6. And our units are meters. Contrast that with this one. Find the total distance traveled from t equals 0 to t equals 5. So total distance is the integral from 0 to 5 of the absolute value of v of t dt. So that we are going to put in the calculator as follows. Why don't I put in what we're putting in? Absolute value of t squared minus 4 dt. And I'm just going to use the finite integral again here. And the way that I'm going to enter it looks like this. It's going to be finite integral, and then it's going to be ABS, and I'll show you where to find that in just a second. T squared minus 4, comma t, comma 0, comma 5. And what you do is you do your normal math 9, and then on these calculators, let's see where to go. It's under math number. Yes, math number, that's the absolute value. You can see it right there. So I'm just going to hit 1. Now I've got the absolute value. Now I put in whatever I wanted. have variable squared minus 4. Close that parenthesis to close the absolute value. Then, like normal, comma variable, comma 0, comma 5. And it's going to take a little bit longer to chug away. There we go. Notice this is not the same as this number made positive, especially because this is already positive. This is taking into account that the particle traveled to the left a little bit and then undid that travel coming back to the right. That is not counted up here in the net, but it is counted in the total distance traveled.